get to revision question 2. Let's see what this entails. So sketch below is the graph of f of x, all equal to k to the power x, where k has a value greater than 0. We also get given a point, 4 and 16, which exists or lies on the graph of f. Well, that's enough. We can see we have a y-intercept over there. It's pertinent information. And then we are asked to determine the value of k. Now, why did I say this is pertinent information? Well, it means there's no value in front of k, or no modifier. So the a value is equal to 1 immediately. If we take our standard form to be a times b to the power x minus p, and that's of course for any f of x, which is meant to be a exponential function. So, well, for the value of k, all we need to do is punch that value into this function. So for number 1, we are going to calculate f of 4, and we know that it's equal to 16, into the graph that goes, which means our y value is 16. K is still k because we need to figure out what that is, and that's to the power 4. Well, 16 can be converted into exponential form, so that's 2 to the power 4, and then obviously we have k to the power 4. As we can see over here, if our exponents are the same, we can state that the bases are the same. So there we have that. K is equal to 2. The graph G is obtained by reflecting f about the line y is equal to x. So that's what they mean graphically. Algebraically, they're just telling us G is the inverse of f. Determine the equation of G in the form y is equal to. Well, we do know that f of x is now nothing other than 2 to the power x. Now, for g of x, we can then say x is equal to 2 to the power y, and if we want to make y the subject of this equation, all we need to do is convert exponential form into log form. So the answer to a log is an exponent being equal to, well, the log of something. Well, the base remains the base, and then that x is obviously going to be our argument. And there we have that. 5.3, sketch the graph of G, indicate your coordinates. Indicate the coordinates of 2 points on G. Well, the first point is quite easy. We're just going to transfer that, and then we can transfer this point. Now remember, when I transfer this, that coordinate is actually 0 and 1, as opposed to this one being 1 and 0, because for any inverse, the coordinates just switch, which means what I'm going to do here is just have coordinates 16 and 4. Yeah, let's move it right over there. Now the second thing we do is to realize, hey, this is an exponential graph. It has an horizontal asymptote. So allow me to just lightly, or not so lightly, just throw in a hypothetical vertical asymptote, because that gets inverted as well. So for f, we have a horizontal asymptote, and for g, our inverse, we have a vertical asymptote. Now it's a question of just tracking what's happening with the original graph. As we can see, that the graph's asymptote, the graph approaches the asymptote towards negative infinity. It's negative infinity, infinitely to the left over there. Well, where's negative infinity for our inverse? Well, it's going to be negative infinity exists there, which means our asymptotic approach needs to happen in that direction. So that's about as smooth a curve as we're going to have this early in the morning. Anyway, that is good. We have our points indicated, the 2 points that they asked for, our bare minimum, but I think that is more than enough. Use your graph to determine the values of x for which f of x times g of x is greater than 0. So let's just remind ourselves where our initial graphs were. So we had that. We can do that better, quite a bit better. So that's 1 and 0 right over there. So what we want is for this product to be positive, and we can see we already have the y-axis to indicate one important point, and then we can just delineate this with a dotted line to see that any value to the right of 1 or greater than 1 is going to be positive. Now for both g and for f over there. How about between our asymptote, our vertical asymptote caused by g, and this value 1? Well, that's just going to be a negative y value and a positive y value that we get from f. Therefore, that product is going to be negative. So if we want this positive product, well, the answer to this question is just going to be x needs to be greater than 1, because that is where that happens. Now we want to know where g of x is less than negative 1. So where does that happen? Well, if we can have a look over here, this is where g of x becomes less than 0. Well, at some point it crosses the value, or goes past the value, negative 1. Now we want to know where that is. Now, graphically, we can have a look at this, and it should be able to see that it should sit somewhere where x is equal to a half. It should happen at roughly a half if we look at the structure of the of our inverse equation, because g of x is equal to log base 2 of x. Radio. So how do we write that down? Because we need to know where it's less than negative 1. So the 1 value is this boundary, okay, which is 0, and this is for number 5, and that's just going to be greater. X is just going to be greater than that, and as we said, it's where x is less than a half. Radio. If h of x is equal to f of negative x, calculate the value of x for which f of x minus h of x is equal to 15 over 4. Well, first, let's get h of x. Well, h of x is what they say, f of negative x, which is just going to be equal to 2 to the power negative x, because k's value, as we determined, is 2. So we can just sub a 2 in there, and then the x becomes negative. So what do they want? Well, they want f of x minus h of x, and then they give us a total of 15 over 4. Well, it's just base substitution, so that's 2 to the power x minus 2 to the power negative x, and that's all equal to 15 over 4. We can then have a look at this term and convert that into 1 over 2 to the power x based on our exponent laws, and that's just 2 to the power x, and that's all equal to 15 over 4. Now if we use substitution, because we see that these two elements are exactly the same, we can say, well, let k equal 2 to the power x. That's going to turn this equation into k minus 1 over k, and that's all equal to 15 over 4. Multiply the entire equation by k, and we get k squared. Well, that's just going to become a 1 minus 1, and this will of course be minus 15 over 4k. It's all going to be equal to 0. Remember, we just transposed and did the multiplication. So let's get some space going. Because we ran out of it. It's just poor planning from me. But anyway, if we take that over, we multiply everything by 4. K squared becomes 4k squared. That was the point, to get rid of that denominator. So we have minus 15k, and minus 1 times 4 becomes minus 4. That's all equal to 0. That's a bit easier to handle because we have 4k. 4 looks nothing like before. Now it does. That's 4k. There'll be a k in the second bracket. That's all equal to 0. We'll need minus 16 from that product and a plus 1 from this product. Therefore, using a zero product rule, 4k is equal to negative 1, or k is equal to 4. That means k is equal to minus 1 over 4. And that is obviously that. Now, let's just do back substitution. Therefore, we have 2 to the power x being equal to negative 1 over 4, or 2 to the power x being equal to, well, 4 is equal to 2 to the power 2, so let's just fix that immediately. This we now has no solution. And we have the graph of 2 to the power x over here to see what that means. There is no y value less than 0 for f of x, or for that power. There is no y value that is negative. That's why we have no solution. For this one, we know that x is going to be equal to 2 because the bases are the same. And that is the solution to that. So, neat little grade 11 style substitution equation hidden in a graph or function question.